Welcome everyone after the break. I would like to introduce Ilja van Sprudel, who is going to talk about Linux desktop insecurity. And if you, just a reminder that you have any questions, just please raise your hand and I'll give you the microphone. Thank you.
Okay. I guess good morning, everyone. My name is Ilja van Sprudel, as was just announced, and my talk is Assessing the Linux Desktop Security. So who am I? I work for a company called IOActive. I am their director of penetration testing. I do code reviews, penetration tests. Basically, I break stuff for fun and profit. The whole talk is kind of I started doing this for a little while in December, and I made some observations, and I found some problems in Linux desktop. And then I dug a bit further, and I saw a few more things here and there, and I'll sort of give a summary of all the issues I found. And then hopefully I'll be able to present like a solution or two, or potential solution to some of the issues that I found. So what to talk about, I mean, it's quite simple. It's the local security of Linux on the desktop. And so why am I talking about this? Basically, I used to use Linux as a desktop on my main machine, and then I switched to Windows about 7 years ago, mainly for work reasons. I've used it sporadically since then. I've SSH'd into a bunch of boxes, but for the last 7 years, I didn't run it locally on my machine. And I did so in December of last year, and I played with it and I installed it. And it's interesting because a number of things have changed from what I remember. So I installed Ubuntu in late December last year, and it boots into a GUI. And it doesn't look like the X that I'm used to. It looks a little bit more advanced in the sense that it looks like something that non-tech users can use, whereas before, you have a console and all those kind of things. And if you give that to my grandmother, she doesn't know what to do with it. But if you give her what it looks now, they could actually use it. So I spent a fair amount of time looking at local desktop security of Ubuntu. But I also looked at a bunch of other Linux distributions, including Fedora, OpenSUSE, Knoppix. And I took a very, very quick look at some non-Linux desktop stuff, like OS X and OpenSolaris, where I found similar issues, but it's not really stuff that I'll be covering today. This is what it used to look like, right? This is X as we know it. 10 years ago, if you boot into stuff, it looked like this. Now, if you install Ubuntu, it looks like this. And when I first booted into this stuff, I was a bit confused because, where's my console? I want to have a prompt. I want to type stuff. So I took a while to find that. But you got Firefox, you got LibreOffice, you got pictures, all the stuff that end users and consumers would want to use. And yet it's still, it's a Linux desktop basically. So it shows that these distros are quite serious about trying to have their OS on the desktop, whereas 10 years ago that wasn't the case. Initially, I had about a week or so to play with this stuff. What I started off doing is I want to do a little bit of simple entry-point analysis, and so I did a few of very simple command line tools to find some entry points. And then I read a little bit of code just to get an idea of how good or how bad things are. There were a set of problems that I found, and then at the end I'll have maybe a solution or two, or a few things I'll talk about where you can sort of mitigate some issues. So what I actually did, as I mentioned, I ran a bunch of very simple command line tools to get an idea of what the entry points look like on a basic Linux desktop install. So I want to look at shared memory, so IPCS. I want to look at UDP, TCP, Unix sockets, all the stuff that's installed by default, which NetStack gives you. I want to look at cron scripts. I want to look for writable files. I wanted to enumerate, obviously, suid files. And then the other thing I looked at is, and this is kind of funny, because so the last time I used Linux was about 7 years ago, and Dbus didn't exist. And so somebody told me about, what about this Dbus stuff? And I was like, what's Dbus? And I had to go in and look and see what Dbus is and figure out how to enumerate entry points on Dbus. And so it's the command line there. It's a bit more verbose than the other one because it's not, an original Unix utility. It's much, much newer. So I know, doing Linux as a server install, on a default install nowadays, we know it's pretty good. We know it's been relatively secured. We know it doesn't open up a metric fuck ton of ports anymore. We know they've secured a bunch of stuff. We know they've reduced the list of SIDs. We know people have gotten things locked down relatively well in a default server install. And because of this, I assumed my experience was going to be pretty boring, and I was going to come up pretty much empty-handed. Turns out I was wrong. I got varying results for varying distros, but in general, overall, things were not as good as I expected them to be. And so my first question was, well, these are simple command line tools. Isn't anybody, if I was one of these distros, wouldn't I run the same tools, do trivial endpoint analysis, and find the same things that I found before? So overall, the kind of problems I found, I can't disclose all of them yet because some of them haven't been fixed, but some have just gotten fixed, so I can talk a little bit more about those. But in general, it's the things that you wouldn't expect are there, but there's world-writable shared memory all over the place, world-writable shell script and install scripts, incredibly bloated suid binaries, misconfigurations. So in that 1 week of just sort of poking around a little bit, there were over 60 security issues that I sort of stumbled over. The talk isn't about any specific bug, it's just the entire range of them, and the fact that they're so incredibly easy to find that I sort of want to draw some attention to. So the first thing I looked at Dbus, and I showed the earlier command to sort of get an enumeration. It's relatively new attack surface. It's stuff I didn't actually know until I poked at it early this year. Originally, it came from the people that do the graphic stuff, Xdmcp. It's basically an IPC mechanism to get information about your current system or your current session. If some device gets plugged in or something like that, there'll be a message sent across, and then whoever is listening can see, oh, you just connected a new printer or something like that. So there's basically the session bus and the system bus. The session bus might not be that interesting. It's all, you have to be the same user, you have to be the same session. The system bus is, of course, very interesting because anybody can connect to it, and there's a whole bunch of services listening and that you can connect to on a system Dbus, and that you could potentially play with or get info leaks from or that kind of stuff. So, basically, there's loads of new attack surface, and there's I guess, three sort of things that in terms of attack surface. There's going to be configuration issues. You'll have some design issues where you might expose too much information, that kind of stuff. And obviously, you're going to have implementation issues like buffer overflows and that kind of stuff. If you just sort of start looking around for these things, on any default Linux distro, there's going to be anywhere between 40 to 60 services listening on the system bus, which in my mind is a ridiculous amount, and yet they're all there. And all you have to do is look at the configuration file, and you get an idea of all the system Dbus services that are running. And cool thing about the configuration files is it's sort of, it's kind of un-Unix-like because it's an XML config file, and it tells you who can access it and under what circumstances. It's in etc Dbus 1, and then whatever files are in there tell you what services are there. And if you look at if you look at past issues, there's been a few in Dbus. This is one that I linked to. It looks like this. It's basically, it was a bug in a configuration file. And the way it works is if you want to do deny or allow rules in these config files, is that you have to do the entire allow or deny rule in sort of one tag. If you split it up over several ones, it doesn't quite work as you want it to, and that was the bug here. They would say, well, you can do a method call to these destinations, except they split it up over two, which basically means you can do a method call to anything you want. That got fixed, but it gives you an idea of sort of how fickle these things are and how easy it is to make mistakes in just a configuration file. And when I was looking at this, so a couple of years ago, I spent some time looking at mobile application and Android security. And these kind of particular things reminded me a little bit of manifest files for Android applications. And the similarities in configuration mistakes looked very similar. So it was just sort of an observation I made. Once I sort of got an idea of what the Dbus stuff, I wanted to move on to some other things. And of course, one of the things that I always like to do when I log into any Unix system is get a list of all the set user ID binaries and then just sort of get an idea of what they do. And it turns out, actually, even for the desktop, the list was fairly trimmed down. There were, the usual suspects there, like SU, password, and so forth. But the list wasn't enormously long, so that was good. And then I was like, well, let's just see. I mean, it's good they have a shorter list, but maybe I want to know exactly what's in there. And so I wanted to see a list of libraries that some of these SUIDs have. To do readelf -z, and I get a list of all the libraries, because, I mean, they're basically attack surface, right? They take environment variables, there's APIs in there that will take a varying amount of untrusted data that comes from an attacker. And that was a very varied result. Some just use lipsy as they should. Others have piles and piles and piles of libraries that run as elevated users. Some of them have like enormous network parsers that parse piles and piles of binary network data. For example, anything that's X-based, that's SUID, will do so. And so with that, I for example, did readelf -z on KP. And, it gives you libc and libsdc, and those are all good. And then it gives you libqtgi and libkd core and lib whatever. And I mean, the list goes on and on and on and on. And this is all of this runs in an elevated context. So that's an insane amount of attack surface right there. And then I looked at one of the GNOME games, which happens to be GID Games. And again, it's very similar, right? So it's a incredibly long list of a whole bunch of libraries. And because it runs in elevated context, all of that stuff is now attack surface. I mean, in glib, some SVG parsing, GTK, GDK, and a whole bunch of these. I don't trust any of them, by the way, so this kind of scared me. I spent a little bit of time zooming in on X. And for those who aren't that familiar with it, X is sort of this client-server protocol in the way that you use a GUI on most Unix machines, including most Linux distributions. It's a network service, so it can use TCP/IP or IPC, and it can use some shared memory as well. The whole thing is a binary protocol. And basically the SUIDs I'm talking about, so this one and this one, they're X clients, so they connect to a service, and then they take a whole bunch of binary blobs, basically, and they start parsing it. And how do you make them connect to your arbitrary service? There's an environment variable that you can set, which is display, and if you set it to your own service, it goes and talks to that X service. And while the general assumption is that the data comes back from X is, well formed, there's no guarantee. I can point you to a malicious X server and send you all sorts of malicious crap, and you should be able to handle it. This is kind of in a nutshell what the X architecture looks like, right? So here you have the X server, and that's kind of because it's sort of in reverse X, right? So the server is really the client's the server. So this is the X server, and what that means is that's the thing that displays on your screen. And then your applications, let's say Xterm, uses XSleep, and that's the client, and it connects to the server, and it says, render this for me, or do this, or do so and so. And then the X server takes it and makes sure that it comes on your screen. So I looked at the X client libraries because that's the attack surface here, right? If you have a set UID binary and you point it to a malicious X server, you're going to use the X client libraries for the actual network communication. And so that's what I looked at. I spent about a day and a half looking at the network parser in XSleep. It is unbelievably bad. It's a binary protocol parser written in C. Most of that code was written in 1984 till 1988. All of that stuff was written by people at the time, they didn't care less about security. They didn't know what a trust boundary was, much less do any kind of input validation. The moment you lay eyes on that code, you go like, whoa, can't believe it's that bad, but it really is. And so I found, over 60 issues there. Just sort of, I don't want to go into anyone specifically, but just sort of want to give you a small rundown of some of the issues that I did find. So this was, so basically what I did when I started off this stuff is I looked for _X reply, which is basically an XSleep API that wraps around read from the network. And then whatever comes back is that's just data. None of that's been validated, right? So for example, this rep variable contains just binary blobs, and they read values from it, and then they go like, oh, that's a length field, and then they read into other data, and you get memory corruption. Integer overflow, unvalidated index, unvalidated length field, integer overflow, integer overflow, integer overflow, integer overflow, unvalidated length field, integer overflow, integer overflow, integer overflow, integer overflow, unvalidated length field, integer overflow. I mean, and it goes on and on and on and on and on. Sign-this bug. I mean, this stuff goes on and on. And this is just a small sampling. I mean, the list was much, much bigger. And it's just like you start reading this code, and like every other line of code you read, you go like, oh, there's a security bug right there. So it was unbelievably bad. So when I did discover those bugs, I reported them to the X security team, and they've been really good about it. They actually released a massive advisory last week, and they fixed all of them. The developer involved that I had conversations with was actually, I mean, that guy was just fantastic. His name's Alan Cooper-Smith. He has an incredibly deep understanding of X and the protocols involved, and including the code. And he seems to have a good grasp on the bugs that I reported. There's absolutely no pushback. He understood every single one of them, and he's like, yep, that's a bug, I'm going to go fix it. And there was no hand-holding. Like, he knew exactly how to fix it, when to fix it, where to fix it. And he fixed it fast. I mean, this guy worked tirelessly, right? He had to make 104 patches. They did reviews and tests, and all of that stuff was done within 3 months. So I thought that was pretty impressive. And the other thing was, Alan made a few interesting comments. So for example, he said, I don't know how many SetUID X clients still exist these days, but since we know there's more X clients out there that we can keep track of, we have to assume there's still some out there. And then he said, it would be a good idea to put a reminder in the security advisory that best practices are to separate out parts of the application that require elevated privileges from the GUI to avoid these kind of issues. GTK requires this, but not all toolkits do. So XSleep, for example, doesn't. And it turns out there actually, if you go look for them, there's still a fair amount of SetUID binaries that use X in some way. But nevertheless, this is good advice, and it shows that the man clearly has good insight and knows, what you should be doing and what you shouldn't be doing. And then he had some other comments on the bugs I reported. It says, when he had to look at the XKB stuff, which is the stuff that uses all these unvalidated indexes, which it was incredibly bad. He goes like, well, shoot this developer for not freeing us for it yet, and then shoot anyone else who tries to fix this stuff before it's too late for them too. And then, as he's reading over these bugs, he goes like, well, my initial analysis of the first part of XSleep, it was so-and-so, and I stopped doing that, and, and I got so tired, my head started spinning and trying to figure some of these bugs out. And then, some of these bugs, well, if you got anywhere near 4 billion rectangles in your window, what the hell are you doing? And some of these bugs required a fair amount of memory, right? Some of them would succeed. So the way XAPI works is it just keeps taking data. And so if I send you 2 gigabytes of data, it will take 2 gigabytes of data. Except, of course, if you can't allocate it and you would fail. And so basically, one of his comments was like, well, yeah, some of these bugs seem feasible. Much more now than when the code was written, because in 1984, there was no way in hell you could allocate 2 gigabytes of data with one malloc, but now, of course, you can. So there were a bunch of these bugs that were, I guess, would have been purely theoretical in 1984, but today are very, very, very much a reality. This was when the advisory came out about a week ago, there was a post about it on LWN, and one of the comments was kind of interesting because it was a comment by one of the original developers of the X protocol bindings, and I sort of want to quote a little bit from what he said because I found it very fascinating, and it gives some context on why that big of a stream of that trivial bugs are still there. And so he starts off saying, all I can say is, this was 1984, and it was a very, very different world. Over 25 years ago, there were no bad guys on the internet, at least. I remember the Morse worm hitting, and I remember Kevin Mitnick, and all those things happened after I started writing those protocol bindings, or they hit as he was writing them, basically. Some of these bugs I clearly wrote in that period, and others copied my mistakes. Others just couldn't And then he says of some of the bugs, they just couldn't happen in practice on machines of the day. So he was using a 2 megabyte microfax, which is ancient now, but I guess back then that was what you would use. And so this to me gives a very clear historic context of some of these bugs. One of the other things I want to sort of call out on is, so when the advisory came out, so the way it worked is, so Alan, I sent the bugs into Security, and Alan spent about 3 months making all the patches, 104 of them. And then when they were done with those patches, and they had done a little bit of testing, and they had reviewed them, they went to, I think, like some security mailing list, and you can basically, and it's all the vendors subscribe to it, and you can send in a bunch of bugs and get them sort of embargoed for 1 or 2 weeks. And he said, well, because of the long list of bugs, we'll do a 2-week embargo. We'll give the vendors 2 weeks to merge into patches, and then we'll release the stuff. The embargo expired May 23rd, and May 23rd, the X guys, on 8 in the morning, US Pacific time, they released their advisory, and all these vendors had 2 weeks notice. 2 weeks is a relatively short time to merge in 104 patches in a code base you don't own. And so Debian's turnaround was ridiculously fast. They had 104 patches to merge in. They did it in 2 weeks. They had full releases and full advisories on the day the embargo expired. Nobody else managed to do this. Only Debian did so. And if you look at the advisories and the work done, and I've had a little bit of email exchange, there's this guy named Moritz Mühlenhoff, and I think he deserves most of his credit. I mean, I don't think this guy slept in 2 weeks, because there's no other way to do it, I think. But I was stunned at Debian's fast turnaround on these bugs. But that's RawX, and RawX, turns out, isn't actually used that often nowadays. What happens is you build libraries on top of RawX that are easier to use and that support a whole bunch of stuff that RawX doesn't. And then you use those libraries as a developer, and those libraries call out to RawX APIs, basically. So some of them, obviously, we know, right? Just GTK, GTK Plus, KDE, Qt, and then every so often they'll make rare calls to XSleep code. And there's others, right? There's Enlightenment and a set of other ones as well. So once I had sort of looked at the XSleep code, I sort of moved on from there, and it's like, well, I wonder what KDE looks like, and I wonder what Qt looks like. And it turns out, security-wise, they're pretty much on par with X. It's not very good, very, very trivial bugs, and they would look like this, which is basically, a stack smash. They look like this, which is a delete of a non-nude pointer, and it goes on and on and on. So, if I run across these bugs and I, go look up what the vendor is, which is Qt in this case, and I report them to Qt. Their security team were very different than the XOR security team. They're like, well, we don't consider this to be a security bug. I didn't agree with them, and I think the quote from Alan, specifically this one, is just very much dead on SUIDs that use X. And so, anyway, the Qt team did not agree with me at all, and so I had a small email exchange with them, and they go like, well, KDE is precisely one set UID, so and so and so, and there is a good reason for that, because we don't consider that. It would be a security bug if you use us on an SUID context. And then he goes on to say, well, because as the way I see it, if you did do that, the most obvious attack surface would be malicious styles. And then I get the mail back and go like, hold on, did I just get 0 day from their security team? And so I question them on that, and also say, well, I think there's more than one X SUID out there. And so I get a response back, and they go like, well, if there are more than that one X SUID binary, then that would be them using our libraries would be a security hole in that application. And then I ask, well, do styles really contain executable code? He goes like, yes, they do. I'm like, oh well, fantastic. I'll go see how I can make malicious styles then. And I question, for example, on KPP because I know, for example, Ubuntu has an SUID. And the guy goes back and says, well, it shouldn't be. There's this frequently asked questions about KPP, and it says this and this and this, and I doubt any distros would ever install SUID. And the quote goes, there's no need for the set UID bit. If you know a bit about Unix system administration, simply create a modem group, add all users you want to give access to the modem, that group, and make the modem device read writable for that group. Turns out that code is not complete. If you the sentence right after it goes, but the KPP team has lately done an awful lot of work to make KPP set UID safe. It is up to you to decide if you install it and how you install it. And sure enough, if you look at Ubuntu, there's KPP and it's suid. And that runs Qt KDE on top of that. My main issue with this was basically is that if you're making a library, you shouldn't be setting policy in how people should be using you. I mean, you have developer documentation. You try to develop it document it as good as you can. And you make sure you validate length fields and that kind of stuff that come in. And the assumption is, of course, that when a pointer comes in, the pointer is valid. That's as far as your assumptions can go, right? Anything else than that, you have to just be very defensive about it. Qt isn't doing that. They don't see it that way. And they're kind of sitting on the fence. They're saying, well, just don't use us because that would be a security violation. I think that's too easy, right? It's basically you're sitting on the fence, you're not doing anything because it's just too easy, because it's easy. And so my view is, you either defend this stuff and you don't bitch about it, or you basically go like, listen, you're running suid, I'm just going to call exit, bam, get it over with. Either one of those would work. But they're not doing either one of them. They're just sitting on the fence. None of the bugs got fixed, the ones I gave you, so that's 0 day right there. But what was really cool is that I got the okay from the GTK Security team to disclose those 0 days. So I asked them, since you guys don't think it's a security bug, do you mind if I talk about this publicly? And they go like, no, go right ahead. So there you go. It's nice that when you get security teams to okay dropping 0 day on them. Another thing I noticed is, so when you generally run an executable under Linux or most Unix systems, when you use the dynamic linker, it knows about environment variable called LD preload. And what that means is you can sort of preload a bunch of shared objects, and they'll get run when the application runs. LD preload itself has been made setuid safe many, many, many years ago, and it's had a set of problems, but it's more or less safe nowadays. KDE and Qt and GNOME said, well, we must have something like that too, specifically for Qt and GTK modules. And sure enough, they made Qt plugin pat and GTK modules, and neither of them are setuid safe. If you have a setuid binary that uses KDE or GNOME, and you set those environment variables, and you put them to a shared object, they'll load it and they'll run it. The GTK stuff is slightly more complicated, right? They seem to be doing somewhat better than the Qt team. And so they have a web page about it, and they say they don't allow GTK plus, suid GTK plus applications. And I mean, it's too small to read, but I have the link on top, and if you want to read it, you should go to the web page and read it. It's actually, so I have a small quote from it. If you read it, it's actually very beautiful, it's well thought out, it's incredibly sane. Whoever wrote that had a very, very decent grasp of application security. And so one quote from that webpage is, the security of GTK Plus requires the security of XSleep. The GTK team is not prepared to make that guarantee, which is a good thing because we just saw very earlier on that there's very, very trivial bugs, over a large set of very trivial bugs that are in there. So that to me sounded really, really good. And then I'm like, well, before I just believed them, why didn't I go look at their implementation and see what they do? And so when you use GTK and you call their init routines, they'll have this function called check_set u GID, and there's a comment on top, and it says, this check is to see if a process is running suid or sgid at the current time. If so, we don't allow GTK Plus to be initialized. This is meant to be a mild check. We only error out if we can prove the program is doing something wrong, not if they could be doing something wrong. And so for this reason, we do a very mild check and not the check we should be doing. And so what does that mean? In reality, it means you can have an suid binary, suid root binary that uses GTK plus. However, you have to acquire all the privileges you want first. Then you drop your, so you basically make your UID and your effective UID the same thing, so you drop your privileges. And if you then initialize GTK plus, it's totally fine. Even though you're still holding all these privileged resources, GTK plus will just run, and for example, it'll, if you then give it GTK modules, you can write a module to go steal those privileged resources and do whatever the hell you want with it. So, as an example, right, games are a great example, right? There are tons and tons of SGID GNOME games that are installed by default on most Linux distributions. They're SGID games, they're set group ID, and the reason why is because they have a common high-score database file that that they want to be tamper-proof, so that you can't cheat as a normal user. And so the way that works is the program loads, it goes and fetches, opens the files, read-write file script to the database, drops all privileges, and then reads and writes to the database, whatever your high scores are, basically. So basically, the way this would work is that you could use GTK modules to get and then write some code to get access to the file descriptor for a high-score database file. But because this high-score database file is considered a trusted resource, the parsing of that is not going to be very good because they assume it's trusted, right? So if at any time you find any bug in the parsing of that high-score database file, and you can corrupt it, that means anytime anybody runs that game and they would parse the high-score database file, they could be exploited and you could gain their privileges. So that's just a simple example of how this would work on where you escalate privileges using the GNOME games. I also spent a little bit of time looking at X-display managers. Turns out there are actually an awful lot of them. Apparently every distribution feels they must make their own. It uses this ancient protocol called Xdmcp, which goes over UDP. And most of them have a dependency on this library called libxdmcp, which is part of the Xorg library distribution. So I spent some time looking at the library, and it turns out the library isn't that great. It didn't have any specific bugs in themselves, but the APIs left a lot up to the developer to do. So they easily lend themselves to abuse. So all these APIs, when they would fail, and it would be pretty easy to make it fail, for example, you cut off network connections, that kind of stuff. They leave everything uninitialized. So you would call them, you give them pointers, a bunch of pointers to pointers, and then they fail, and you don't check the return value, and you start, freeing pointers that were never mallocked in the first place. It's not so much as it is a specific bug, it's just that the API is kind of crappy, or at least the error handling in the APIs is kind of crappy. I told the Xorg people about that too, and the same guy, Alan Cooper-Smith, goes like, "Oh yeah, you're totally right. Let me go in and make sure that we fail in a safer way." And then he makes sure that even when they fail, they make sure they initialize everything. I mean, when you fail, you initialize to null, but still it's initialized in some way. So that was pretty cool too. One of the display managers I did look at was a LightDM, because it happens to be the one that Ubuntu uses. And that one's kind of interesting because they have what's called greeters. So LightDM obviously runs it under high privileges. But they have this thing called greeters, which is you can write some code basically that runs that doesn't run privileged, and then LightDM will basically fork off, make a pipe, spawn a new process, and then talk to the unprivileged greeter, right? So there's a clear trust boundary between your greeter and LightDM. And so I started looking at a little bit of that IPC between the two. It wasn't that bad. I mean, it wasn't great, but it wasn't that bad either. There were a number of bugs. The biggest one of them was basically sort of in the communication parsing itself. It looks kind of complicated, but this is the main read function basically. And the way it works is they first read a header, and when they read the header, they call this function again, and then they read the rest of the message, right? So it's read CB, and then they go like, oh, don't have header yet, so they go to header first. And then when they read the header, the first thing they do is they read in the length field, and then they say, well, we'll do a malloc length field plus header size. And of course, because the length you read in, it can be very big, and you can make an overflow. So you do a very small alloc, and the second time you get back into read CB, you have a very small alloc, and then they go like, you read a second length, which says the rest of the message, right? And then that can overflow too, so you get another really small value. And then when the actual read happens is they subtract a header value from it, so you get a very small value for which you subtract a bigger value, so you get a negative value, which then becomes a large unsigned value, which you then use to copy it into a very small located buffer. It sounds a bit complicated, but if you find it interesting and you can download slides and you read the stuff, it takes about 5 or 10 minutes to sort of figure out what's actually going on here. I thought it was kind of cute because it involves 2-inch overflows and 1-inch underflow in order to get it to work. So this is the basic idea, basically. But yeah, it's a bit hard to run over now. But if you find it interesting, you should download the slides and read it. I thought it was kind of a cute bug. So as I mentioned earlier, all these libraries, sort of GTK and Qt and KD, sort of run on top of X. There's also a bunch of apps that will sometimes call the XAPIs directly themselves because they need to query something that those higher level libraries don't support. And so usually the way it works is you want to get some property for some window some way. And they have an API for that called XGetWindowProperty. And XGetWindowProperty is a very, very short wrapper around _XReply. It just takes a bunch of network data and then gives it back to whoever called it, right? And then there's a bunch of APIs written on top of XGetWindowProperty, so it's XGetClassInts and so forth, and they're sort of just built on top of that. But they're all just very small receive wrappers. So one of the things I did is I looked at the use of XSleep APIs in various applications, and it turns out that was pretty bad too. By far, the most common bug was this one, and it's basically you call the way it works is you call XGetWindowProperty, and you give it a pointer to a pointer, which will be initialized with the data that gets sent over network. And then, for example, code like this, the return value isn't checked. So what you could do is if you call this function, then you sever your network connection, and this thing won't do anything, and it returns failure. And what that means is the SF pointer right there is not initialized, but they'll still call a free on it, so you get a free of uninitialized pointer on the stack, which is clearly a bug. It can lead to all sorts of weird memory corruption issues. And this is super, super common. Every application I've ever I looked at that uses this API does it wrong half the time. So it sort of takeaway is that you have to look at its return value. If you don't, you're in serious trouble and you're going to cause memory corruption. Including XSleep had a bunch of these kind of bugs. And so when I reported it to the X guys, this Alan Cooper Smith was like, oh, you know what? You're right, that is a problem. I'm going to go fix those bugs. But what I'm also going to do is I'm going to go back to XGetWindowProperty and make sure we initialize that pointer to null in case of failure. And sure enough, that's what they did. And so X programming is now a lot safer because of this one fix. Obviously, it's always a good idea to check return values. But up until a week ago, this was one of the most common bugs out there in applications that use X, basically. And then, I think, because when I started looking at these applications, it was pretty clear that when people just look up the APIs in developer documentation, they didn't seem to realize that any one of those calls are actually just a receive from network data and parsing of it. So there's a relatively long list of sort of XAPIs that are really just wrappers around receive. So this is some of them. And then these basically wrap directly around receive. And then all of these wrap around XGetWindowProperty, which wraps around receive. And so it's probably about 30 of them or something. And all of these things are basically, if you see them, what you should really think is receive of network data. But really, when you look at suid applications, at least when I looked at them, there's sort of 3 categories of them, right? There's a bunch of config tools. You'll have some games. And then there's screen-locking utilities like XLock and XLock More and XScreenSaver who have to be suid because they have to go look up your password entry to make sure that you give in the right password. Give in the right password when you want to unlock your system. The good thing is most of these apps drop privileges, but before they do, they still go and acquire a bunch of privileged resources. Even the ScreenLock ones do, right? Although if you look at the ScreenLock utilities over the course of the last 15, 20 years have had a slew of vulnerabilities, and so the people writing these apps are like, oh, god damn it, we want to try and avoid this, and so over the course of a couple of years, they sort of tried to scale down the amount of privileges they needed, and they got it down to application runs, application goes and fetches your specific password hash for your specific user, and that's it. It's like one string, and they drop all privileges, and that's all you get. They use on Linux. They would use getsp nam for that to look up that one string. It's basically the string that shows up in your shadow file, right? So that's not much of a resource, and you go like, oh well, that's good. Even if there's a bug in there, there's not much you can gain. Turns out it's not entirely true. I started looking at stuff, and things are worse than it seems. So when you use this get sp name API, what it really means is there's another library called the Linux shadow library who's responsible for handling those, what that API is supposed to do. It goes to your shadow file, reads out the entry, gives you back the entry. But it does a little bit more than that, because the way they do it is they use C file stream APIs, which use heap buffers behind your back, and they spray whatever you read all over the heap, left and right. They reallocate buffers, they resize them, they make them shorter, bigger. Anyway, the bigger the file is, and the more variation there is in the length of the strings, the more it starts spraying this stuff all over the heap. And then those functions themselves, of course, have, before they put it on the heap, they put it on their own stack, and they don't clear the stack or the heap. So basically, when you call this API, even if you need a single string, what it really means is it leaks these things all over the place on the stack and the heap in your address space behind your back. So that was a problem. So basically, my summary for the issues is using XSleep and suid is a really, really terrible idea. You should, if you have one, you should try to move away from that model. GTK Plus also still kind of sort of allows suids to use their library, even though they would say they don't. They really do. The other thing I noticed, obviously, was very, very sloppy misuse of XSleep APIs. And then the last thing I noticed was the Linux shadow library is basically a disgrace. So there's a number of things I didn't get around to do, and I still wanted to do. So I want to look at like some of the package manager stuff and the clipboard. And I didn't really have time for it, but I sort of kind of briefly looked at it for 3 seconds. And it did kind of look bad, right? So what I did was I just, you know, I had OpenSUSE and Fedora and Ubuntu on, and I just sort of install a package and sniff the network and see what goes on. And it looks like this, right? So this is all plain text, HTTP, XML wrappers and that kind of stuff. I find that a little bit scary because you would think at least they would use some kind of encrypted channel. They would use SSL or something like that. They don't. And so it's all plain text, and so just to that, like, it doesn't look very tamper-proof to me. And so you would hope that at least the data they fetch, that they sign it and that they check it correctly, and that they have signatures locally, or if not, that they have a secure way of fetching the signatures. And even if they have signatures, we should hope or assume, or at least hope, that they don't use MD5 check signatures. And even if they get all that stuff correct, which is unlikely because those are places where you make very big mistakes generally, even if you get all that correct, the network protocol is still unencrypted. And that leaves you with a very, very big attack surface you shouldn't be having in the first place. Anyway, these were just very small observations. I don't know if any of this is really true, but it kind of feels pretty bad to me. And then I also want to look at the clipboard. I didn't actually get to it. There's a spec called ICCCM. I didn't even read the entire spec. But there's a very interesting comment on the spec. And if you just, so all I know about that spec is that comment or that rant. But it speaks volumes. You should go read it. If you ever download slides, and you should go to that link. And I have a few quotes from it, right? The thing starts off, oh, you know, dude, that document is devil's spawn. And it goes on, and it gets worse and worse and worse. What about protocol? It goes like, well, yeah, I've seen more elegant protocols in unlikely places. When blowflies fly over a pile of elephant shit, the pecking order is a more elegant protocol than ICCCM. And it goes on and on and on and on about this massive rant about ICCCM. And that's really all I need to know about that particular clipboard protocol. Thank you. So solutions. The shadow thing is easy to fix, right? Basically, you take out the file streams, and you replace them by syscalls, and you make sure you memset everything. And of course, when you memset it, you want to make sure the compiler doesn't take it out. The other solution I had is sort of the what to do with suids on Linux or any Unix, really. And I mean, things like, it used to be everything, an suid would run as root. They would never drop privileges. They would just keep running as root. So if you had a bug, you had a full root compromise. Probably about 15 years ago, people were like, well, maybe what we should be doing is we should acquire privileges and then drop our UIDs. And at the time, that was a really good idea. Nowadays, I don't think that's good enough. It's not sufficient. The model never evolved, and I think it should, because those resources are really the thing you want to go after anyway, and you can usually use those to escalate back to root privileges somehow, right? Read FDs to defkmem, read write to etc resolve, full content of EDC shadow. These resources are usually a very, very big thing. And so basically, what I would propose is to sort of have a model where you sort of combine perf dropping with privilege separation, right? This is the stuff that people started doing in OpenSH, and it turned out to work really, really well. And I think to do it for SUID, for some SUIDs is actually not going to be that hard. And so the way it would look is basically, you make a pipe, you fork, and then the client drops all privileges, the server gets the resources it needs, and then drops all privileges. And then you have a very well-defined boundary between the client and the server that you were to go over that pipe, where the client goes like, do this for me, do that for me, and then the server gets to decide whether or not that's actually going to happen. And this works because the client still retains its SUID bit, so you can't debug attached to it. That model isn't entirely perfect. I think we can sort of make it better, or sort of take out a few things that kind of suck. For example, when you do read alpha on some of these binaries, the list is just enormously long, right? The libqt and whatnot. So you don't just want to fork. What you want to do is you want to do a fork and then an XXV, which flushes the address space, and so all those ginormous libraries are gone. And then you can just pass the file script to the XXV process, and from there start talking to them. And so the only library you really want is the lipsy library. And actually, you don't want lipsy either, because the default on Linux distributions is glipsy, is GNU-libc, and it's unbelievably bloated. It's 100 megabytes source code. It has APIs like memfrob and strfry and all these things you would never ever use, but they're in your address space anyway. And so, in my view, you can't trust glibc. It's too big, too bloated. What you should be looking for some kind of embedded libc, such as dilibc or uclibc or klibc or muzzle or one of those, right? So that leaves one piece of code bloat left, which would be the dynamic loader, which takes environment variables and parses them, and we know they've had problems there in the past. So no dynamic loader, and so the way you fix that is if you have an SUID, they can be only static binaries, period. And that was it for my solutions. So I guess I'm supposed to have a conclusion. Everything I looked at or touched smelled bad and looked bad. So I don't know, run for the hills. I hope people will make it. I mean, there's a lot of work to be done here trying to secure the Linux desktop a little bit. The problem is that none of the things that people are using are really written with a trust boundary in mind. But I hope that people will work on this a little bit, and I hope that some things I pointed out maybe people will fix. Okay, that was pretty much it.
Thank you very much.